Hello and welcome again to my Physical Science online video lecture supplement series. In today's video, I wanted to work through one of the relatively long and complex examples that I have put together as a supplement for the physical science course. That's a supplement for this Introduction to Physical Science text by Shipman, Wilson, and Higgins. This goes with Chapter 5 on temperature and heat. Of course, I have already made a separate video in which I worked through a few relatively short examples, but I now wanted to make a few videos where I work through the longer examples with this chapter. And there are a few relatively long examples in this chapter. I still feel like there should be a separate video to address each of these longer ones, so that's what I'm up to right now. In this example, the question is to calculate the heat needed to change 9 kilograms of ice at 263 Kelvin into steam at 383 Kelvin. So this is actually a relatively complex example because there are actually 5 steps involved, because you have to do this sort of piece by piece. The first step is that you have to heat the ice from 63 Kelvin to the melting point of ice. So 263 Kelvin is equivalent to minus 10 degrees Celsius. So you got to heat it from minus 10 degrees Celsius to 0 degrees Celsius. Then in step 2, you still have ice that's at 0 degrees Celsius, and you want it to become liquid water, so you have to melt the ice. Step 3 is that then you have to bring the temperature of that now molten water from 0 degrees Celsius to 100 degrees Celsius, in other words, to the boiling point of the water. Next, you have to boil the water, basically vaporize it at 100 degrees Celsius, and then you have vapor at 100 degrees Celsius, which you have to raise another 10 degrees to 110 degrees Celsius, which is equivalent to 383 Kelvin. So let's get to it. Times, might as well make the conversion factor to joules in here. So times 4,186 joules per kilocalorie. So what we have here is 80 times 9 times 4186. So this looks like 3,013,920. So I'm going to go ahead and write that down here. Whoops. All right. So 2 steps down, 3 as it turns out to go. So for step number 3, we now need to raise temperature of water. And this is going to be from 0 degrees C to 100 degrees C. So delta T is 100 degrees C. Again, this is going to be using heat equals mc sub p delta T, and C sub p is 4,186 joules per kilogram degree C, and that's table 5.1. So the heat for this step, therefore, is 9 kilograms times 4,186 joules per kilogram degree C times 100 degrees C. So the heat for this step is going to give us 9 times 4186 times 100. So this is 3,767,400 joules. So step 3, 3,767,400 joules. Step number 4. Step number 4 involves vaporizing or boiling. So boil the water. And the latent heat of vaporization from table 5.2 is 540 kilocalories per kilogram. So the heat for step 4 is going to be 540 kilocalories per kilogram times 9 kilograms times that conversion factor, 4,186 joules per kilocalorie. So the heat found for step number 4 is going to be 540 times 9 times 4186. So this is 20,343,960. So step 4, 20,343,960 joules. Okay, step number 5 is raise the temperature from 100 degrees C to 110 degrees C. And that's steam, so specific heat capacity should be, and this is from table 5.1, about 2100. So actually about the same as with ice. And that's joules per kilogram degrees C. Okay, so heat for step number 5, therefore, is 9 kilograms times 2100 joules per kilogram degree Celsius times 10 degrees Celsius. Again, this is using the equation heat is mass times specific heat capacity times change in temperature. So now let's plug these things into our calculator. 9 times 2100 times 10, and you get 189,000 joules, which is good news because that's actually what we got for heat number 1, which was reason why that's such good news. This again is as a double check, is because for heat number 1 we had the same amount of mass, the same change in temperature, and the same specific heat capacity, so we would expect to get the same answer. So that's a way to check against calculator errors. Okay, so here's a summary of what we've done so far. We have started by raising the temperature of ice to the melting point. That was 189,000 joules. Then we melted the ice to liquid water, 3,013,920 joules. Then we raised the temperature of water to a boiling, so 3,767,400 joules. We boiled the water to make steam, 20,343,960 joules. And we then raised the temperature of the steam to the final temperature, which cost another 189,000 joules. So to finish the problem out, we need to have a step 6, total heat, which I'm going to label as H total, is going to be the sum of these heats that we used in the previous 5 steps. So H1 plus H2 plus H3 plus H4 plus H5. Okay, so that means that the total heat is 189,000 joules plus 3,013,920 joules plus 3,767,400 joules plus 20,343,960 joules plus 189,000 joules. So the total heat, therefore, let's get out our calculator because it's time to do this. So 189,000 is our first one. So that plus 3,013,920 plus 3,767,400 plus 20,343,960 plus 189,000. So this gives us our total, so 27,503,280. Since we only have so many significant figures to work with, actually we started with 4 significant figures. We should probably round this off to 4 significant figures. And that makes it 27,500,000. And so that's the total energy needed to bring this process to completion from initial temperature of ice to final temperature of steam. So that seems like quite a bit of heat, actually. Of course, recall that the power companies bill you by the kilowatt hour, and that we found the kilowatt hour in the previous chapter as 3,600,000 joules. So, this is maybe 8 times that much, and so this maybe cost about 80 cents to do if you could get all of the energy from the power company and convert it into this heating and melting and boiling process.